You tap your phone's glass, and it reacts instantly, as if it somehow knew exactly where your fingertip was the moment you touched it. There's no hidden camera and no magic, just a transparent, invisible grid of conductive lines under the surface, constantly measuring tiny changes in electricity caused by your finger. This is the principle of a capacitive touchscreen. Before modern touchscreens, many devices used resistive technology. Those worked by stacking two thin conductive layers separated by a small gap. When you pressed down, the layers physically touched, changing the electrical resistance. It worked with almost anything, a pen tip, a fingernail, or even gloves, but required pressure, reduced image clarity, and didn't support smooth, multi-touch gestures. Capacitive touchscreens, which dominate today's smartphones, tablets, and laptops, work completely differently. They use a grid of transparent electrodes, usually made from indium tin oxide, arranged in horizontal and vertical lines. One set of lines sends an alternating electrical signal, while the other set measures how much of that signal is transferred at each crossing point. Your finger, being conductive, interacts with the electric field, slightly reducing the signal's strength at specific intersections. The touchscreen controller detects these changes and calculates your exact touch location with extreme precision, often scanning the entire grid hundreds of times per second. This design supports true multi-touch. It can track multiple points at once, so you can pinch to zoom, rotate an image, or use advanced gesture controls. The same technology allows palm rejection, where the system detects the large, slow contact of your palm and ignores it while still tracking a stylus. Passive styluses mimic a finger's capacitance with a larger tip, while active styluses send their own modulated signals, enabling fine tips, pressure sensitivity, and tilt detection. There are challenges. Regular gloves often block the electrical connection because they insulate your finger from the screen. Special touchscreen gloves have conductive fibers to let the signal pass. Water can cause ghost touches because a thin film of moisture connects multiple electrodes at once, confusing the controller. And if the conductive grid is physically broken by a crack cutting through a trace, you get dead zones where touches no longer register. Touch responsiveness depends on the sampling rate, how often the grid is scanned, and the display's refresh rate. Gaming devices push both as high as possible, sometimes scanning at hundreds of hertz, so the image feels almost glued to your fingertip. So the next time you swipe to unlock your phone, zoom into a photo, or draw with a stylus, remember that beneath that sheet of glass is a sophisticated electrical system running silently at high speed. Every millisecond it's sending signals, reading responses, filtering out noise, and deciding which contacts are intentional and which to ignore. It's translating the invisible language of capacitance into precise, fluid motion on your screen. Touchscreens have become so natural that we rarely think about them. They simply work. But each tap is a tiny physics experiment, relying on the conductive properties of your body, the sensitivity of microscopic electrodes, and the power of a processor tuned to interpret them. It's a perfect blend of material science, electronics, and software design, all condensed into a layer thinner than a human hair. And maybe that's the real magic, not that it reacts when you touch it, but that it's been engineered so well that it feels like a direct extension of your hand. In a world full of complex machines, the best ones are the ones that disappear into the background, leaving you to simply reach out and interact without ever thinking about the science happening just beneath your fingertips.